Hello everyone, let's do 3.7, which is called optimization. It's primarily word problems that generally deal with maximums and minimums, which means you need to know a general equation or relative quantities to each other, possibly make a sketch in order to find maximums and minimums. We know that this is going to require a derivative, but ideally our derivative needs to be in just one variable. So sometimes you're going to have to use those equations, you know, the relationships, to use substitution to get it into one variable. And then when you take the derivative, you can decide how feasible answers are depending on what's going on. But if you're looking for a maximum or a minimum, that can be determined based on if you're switching from positive to negative on the first derivative or negative to positive. Again, the hardest part about these problems is going to be setting up the equations. So let's just jump into one and see how it works. A manufacturer wants to design an open box having a square base and a surface area of 108 square inches as shown to the right. What dimensions will produce a box with maximum volume? So over here, part of the picture is I wrote what the surface area of this box would be and what we're kind of looking at for the dimensions. If our base is square, that means that the base to length and the width essentially are the same. We're going to refer to both of those as x, and the height we'll call h because it could be different. Now if we're talking about the surface area of a box, it's the sum of all the faces, but keep in mind that the open face on the top means there is no surface area there. So it's one lower base, x times x, plus 4 side bases, which are x times h. Hence the surface area is x squared plus 4xh. So we know x squared plus 4xh equals 108. But we want to kind of know what the volume, we're trying to maximize volume. So my volume equation, which of course would be length times width times height, in our case would be x times h, or x squared h. Now I could take the derivative of volume right now, but as long as we have two variables, that makes it more complicated. So what we kind of need to do is find a way to eliminate a variable in some way. It's most likely going to be easier to solve this equation for h and substitute what x needs to be and take the derivative with respect to x. Otherwise, this equation will be kind of hard to solve for x without having more x's in the terms. So this is what we'll do. Let's try to get h by itself. So we have 4xh, subtract the x squared to the other side. It's 108 minus x squared. And then divide by 4x to get that h is 27 over x minus x. 108 divided by 4. This will be over 4. Let's not lose our minds. 27 over x minus x over 4. And I need to substitute that in for h. So my volume in just terms of x is now x squared times 27 over x minus x over 4. Now if I distribute this x squared, this would be 27x minus x cubed over 4. That will be much easier to take the derivative of. So I'll call this v prime, the derivative of our volume with respect to x. You can call it dv dx as well, is 27 minus 3x squared over 4. And of course, to find max and mins, those are relative extrema, so I need to set the derivative equal to 0. If I add the 3x squared over 4 to the other side, I will get 3x squared over 4 equals 27. That means 3x squared is multiplying the 4 to the other side, 108. And then we divide by 3 to get x squared is 36. Which means if I take the square root, we get x is plus or minus 6. Now one of these makes more sense for a length than the others. Our general feasible region for x is we know that x needs to be greater than 0 because this is a length we're talking about. So I kind of draw my number line to make sure if I've got a max or a min at 6, and I can plug in any value to the derivative and kind of see. So I think the easiest number smaller than 6 to plug in would be 0. Number bigger than 6, let's pick 10, just because. If I plug in 0 to my derivative, it would be 27 minus 0, which is a positive number. If I plug in 10, 10 squared is 100. 3/4 of 100 would be 75. 27 minus 75, definitely negative. So my derivative goes from positive to negative. That's because I'm sitting at a maximum. So it tells me that 6 is a relative maximum. So I know that x equals 6 will help me maximize my volume. But it's not the only thing we've got left. I need to find what h is. So I need to take this 6 and kind of plug it in. So we know h is 27 over 6 minus 6 over 4. These will reduce to 9 halves minus 3 halves, which is 6 halves, which means h is 3. So that gives me the base dimensions, 6 by 6, and a height of 3. So what dimensions will produce a box of maximum volume? Base of 6 inches and height 3 inches. You could also call this dimensions-wise 6 by 6 by 3. Any of those would be acceptable answers. But as you can see, these problems, it's the setup that's difficult, but following through with the calculus is not nearly that bad. So what I want to do is help you set up number 2, but then leave you to try to solve it from there. What point on the graph of y equals 4 minus x squared, where points are closest to the point 0, 2? So over here there's an illustration. We're trying to minimize distance. Now if we know the distance formula relative to the point 0, our distance is y2 minus, or the sum of x2 minus x1 squared plus y minus y1 squared. But in this case, our point in particular, x is 0 and y is 2. So it produces this formula. So this would be x minus 0 squared, so that's x squared plus y minus 2 squared. And as you can see though, that's in 2 variables. But I know a relationship between my 2 variables here, y equals 4 minus x squared, so I can substitute that in for y. So this is now 4 minus x squared minus 2 squared. And if I clean that up, 4 minus 2 would be 2. And from there, I could kind of clean this up by expanding. This is x squared plus 4 minus 4x squared plus x to the 4th, which means I would have the square root of x to the 4th minus 3x squared plus 4. And this is now distance in terms of just x, and I could find the x values by taking the derivative and finding the minimum. Now, relative to the maximum on the last page, we had to go from increasing to decreasing. To find a minimum, you're going to be looking for where it goes from decreasing to increasing. But as I said, as long as you can find the relationships that you need to set up the equations, they kind of flow. But that is going to be the hard part of this, and really every word problem in the math classroom is to put down what you know, the relationships that you know in terms of equations, and figuring out how to use them to get a variable by itself. And this is really all for 3.7.